Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today I would like to tell you a little bit about why numbers are so complicated and everything else is not so complicated. Well, not quite. I'm going to talk about a topic in graph theory, a certain type of limit of line graphs, which is actually in the end a very nice theorem that we could have discovered ourselves. And I kind of would like to discover it live for you. Somebody, of course, has done that already in the 50s. Maybe not, of course, but certainly someone has done it in the 50s. And it's this story that discrete mathematics is, I really love discrete mathematics. It's somehow very, very simple and really nice. And obviously, there's still very hard question in discrete mathematics, but it's certainly much more well behaved than numbers. And this is an instance of this, a very silly one, as we will see, but the theorem itself is still pretty cool. So bear with me, and as I said, we will discover it live using Mathematica code, very silly Mathematica code that I'm going to run, and is also linked down in the description. Okay, so sequences and limits are, I think, a very, very, very classical topic in mathematics. They were around for quite a while. So somehow in the history of mathematics, it was somehow easier for humans to think about numbers and anything related to numbers, and more abstract properties or more abstract structures came much later. So algebras or graphs or everything like that, it's a really, really new concept. So basically everything is somehow modeled on numbers, and then you apply it in a more abstract setting. And very often the abstract setting is actually easier than the one you started with. In particular, I'm talking about something here related to real numbers, and real numbers are a bit scary, at least for someone like me. Anyway, so there's a famous quote by Niels Henrik Abel, so the one from the unsolvability of the quintic, which basically says that, well, divergent series are really, really complicated and whatever. So convergence and divergence and whatever, those topics in classical or number theory analysis, whatever, real analysis, whatever you want to call it, it's pretty tricky actually. And a lot of really, really crazy things happen. So here are just a few pictures, which should look very familiar, obviously. So this is kind of going randomly everywhere and not doing anything reasonable. And then here are some convergence type patterns. And this also converges, if you want, it converges to infinity. So the first one is kind of really, really strange. It's just this divergence, like going up and down. And I'm very, very hand wavy here, what I really mean by that, and whatever. It won't play a role for the theorem itself. It's just kind of a motivation. So this is a very old story, as I said. I mean, limits and whatever played a role in mathematics since its very start, I guess, maybe in a hidden way. So the old Greeks were considering limits in more in a hidden way, as I said. And then later, of course, was Newton and Leibniz and all the calculus stuff and whatever. So very classical topic. And turns out that you can very often do something similar in spirit in more abstract, discrete, or whatever category, theoretical, whatever you want to call them, parts of mathematics. In this case, I just want to zoom into graph theory. And I would like to consider kind of limits in graph theory. And kind of a spoiler, and it's kind of a very general concept, which I can't really put into a theorem or whatever, is that a lot of things that you translate from calculus, from real calculus or whatever, analysis to some discrete mathematics, it's first of all nice because calculus itself is, well, up to the strange behaviors that you sometimes see, is actually pretty nice and pretty powerful. But in particular, if you translate it to the discrete world, you usually get rid of all the technicalities, not really technicality, all the problems that you see in the theory of real numbers or complex numbers or whatever, because, well, as I said, real numbers are pretty scary. And that's what I would like to do. I would like to consider a certain type of limit in graph theory, which turns out to has a really, really simple answer. It's an amazingly simple answer. And as I said, we can discover it ourselves. But now I need to tell you, so we can forget about real numbers and sequences now, and we are now going to graphs. So there's a concept in graph theory which is called the line graph, which I kind of always thought of as being kind of a dual concept, but it's not. And I'm going to explain what it is. So you take a graph, any graph you want, let's say you start with a finite. Let's say all graphs are finite. Doesn't really matter here. And well, something like this. It has vertices and edges as usual. And you want to construct a new graph from it, and it's called the line graph. And the idea is as follows. So the new vertices of your line graph are actually the edges of your old graph. Okay, and that sounds like something you could do. So it's like some version of Poincare duality or something. Very reasonable, like replace vertices, edges by vertices. So here 1, 4 is just the edge that goes from 1 to 4. 1, 3 is just the edge that goes from 1 to 3 and so on. And how do you get new edges? You just look whether the edges share a common vertex. So 1, 4 shares the vertex with 1, 3, and 1, 4 shares the vertex with 1, 2. And 1, 4 shares the vertex with 4, 3, and 1, 4 shares the vertex with 4, 5. So I would like to have 4 edges associated to 1, 4 going to the aforementioned vertices, and that's exactly what it is. Say it again. So the line graph, so L of G, has the following construction. The new vertices of this graph are the edges of the old graph, and you basically look at whether 2 edges share a common vertex, and that's why you put action in the new graph. And what I find very surprising, it's super simple. We'll see several examples in a second. What I always find very surprising, because I think of this as being some form of Poincare duality. So then I always thought I never really looked into it, but I always thought that L of G is actually G again. So if you do it twice, you come back to the old graph, but that's just horribly false. Just be aware. So it's actually so false that I would like to consider the sequence of successively applying the line graph operation. So L to the G is just L of G, L of L of G, L of L of L of G, and then there's just K times. And I would like to study this limit here. So kind of the limit graph, or the behavior of the sequence of taking line graphs and taking line graphs of line graphs and taking line graphs of line graphs of line graphs, and so on. This is now the time to run my Mathematica example, such that you get a feeling for what's going on. And we basically discover the theorem, which we'll see on the next slide. So here's Mathematica, and this very silly code. So basically, list graph just lists all connected graphs. So I kind of don't want to go into the non-connected. Non-connected is boring here, so we can just do it by connected component. It just lists those graphs. Okay, very simple. That's basically it. I would like to have a source where I would like to apply my line operation. A nest line is exactly what it does. It nests m times for a certain input I, and I just take the ith entry on my list. Okay, so I can do something like nest 3, 1, which applies the line operation to the first entry of my graph list. And if I run it, you'll see the following. So this is the entry in my graph list. So GG1 we can compare. So GG of 1 is actually the boring graph that we see here. Just one vertex. So the first connected graph Mathematica knows. And then the rest is the application of the line graph operation. And as you can see, it's not very exciting here. So we start with this graph. We apply the line graph operation. So the new vertices are the edges of the old graph. I don't know. Well, I certainly can't see many edges here. So the new graph is actually empty. And if you apply the line operation to the empty graph, you get an empty graph. And if you apply the line operation to the empty graph, you get an empty graph. So the sequence looks very convergent to me. It just converges basically right. It's just constant basically after the first step. Okay, but we can do the same. So the second graph is a bit more interesting. The second graph on the list is this graph here. And if I apply the line operation, what happens? Well, I get one edge. So I get one vertex, but the edge is not connected to any other edge. So it's just one vertex. And we've seen this sequence before. And now we go to empty and empty. So this converges also very, very quickly. So we do the next one. Well, this graph, it's just 3 vertices in a line. And how does it work now? Well, we get 2 edges. So we put 2 vertices and they're connected via a vertex. So we put an edge. Well, but we have seen this graph before. It just appeared before. So we actually know how the sequence continues, and it converges very quickly to, well, maybe not very quickly, but it certainly converges to a constant sequence, namely to the empty one. And you keep on playing with this, and it's actually not so bad. So this is a more fun example. So this is a triangle graph. So the entry on my list is a triangle graph. And if I apply the line graph operation, if you think about it for a second, you get three new vertices, and they are all connected in exactly the same fashion. So the line graph of the triangle is the triangle. And now we understand the sequence as well, because the line graph of the triangle is the triangle, and the line graph of the triangle is the triangle. So you get triangles, quite a few triangles, actually. Oh, very good. So we have very convergent sequences here. So let's try the next one. This one is funny. So actually, we'll come back to this in a second. It confused me a lot. Like I need 10 minutes to figure out what's going on here. This is an example where a kind of a Mathematica algorithm goes wrong. So we start with this graph. This is sometimes called the claw or the D4 graph, whatever you want. It just has 4 vertices and 3 edges. And we apply our line graph operation. So you should get 1 vertex per edge. So you should get 3 vertices. And now I got very confused, because if I look at this graph, well, we've seen it before. So you should expect this sequence here. But then Mathematica just tells us that the sequence is stable, which is very weird. Okay, but let me comment on this. So let us do this actually. So here's a vertex, here's a vertex, here's a vertex. We certainly have 3 vertices. And well, they're all connected to one another. So this graph is actually a triangle. And Mathematica actually knows that this graph is a triangle. So Mathematica has a built-in function to check whether graphs are isomorphic, which is pretty simple. It just writes basically down the adjacency matrix and checks whether they're related by permutation. And this is just a horrible illustration of this graph here. Let me just copy it, put it here, and it will clarify. It will be clear in a second what actually is going on here, because this is actually a triangle. True. So Mathematica knows that this is a triangle, and just the algorithm, how Mathematica illustrates graphs by putting the vertices, is just horribly messed up. And secretly, there's an edge going from the top vertex to the bottom vertex, which is in the back of the picture, and we can't see it. Anyway, so I got very confused. It took me 10 minutes to figure that out, but it's actually pretty simple. It's just kind of, it's not really an error, but it's kind of still an error in Mathematica. Anyway, back to topic. So then this is clear, right? So the second entry is actually a triangle. It just doesn't look like it. And the sequence stabilizes again because, well, the triangle sequence. Okay, looks very good. Like we've only seen the stabilizing sequences. They either converge to 0 or we have this triangle pattern. And you might wonder whether there's anything else. So let's keep on going. This is a really good example. So we start with the square with an edge, and the line graph operation makes it successively more complicated. So I would guess here that the line graph of the next one is even more complicated, and the limit is actually kind of an infinite graph with infinite vertices and infinitely many edges. Okay, so this the next one. So let's test the next one, and this is one of those again, and so on. So let me just take a random one. What is a random number here? Well, certainly not a random number, but maybe let's take 16. 16 sounds reasonably random to me. There you go. It gets, again, infinitely complicated. Let's do another one. What is another random number? 17 is certainly a random number. And there you go. It gets infinitely complicated. And if we would just test a few more graphs, which is pretty simple, the conjecture would be, well, there are only basically 2 patterns. It either stabilizes very quickly, or it just explodes and you are at infinity. And that is then exactly the theorem, which is actually a pretty cool theorem. So all the difficulties of divergence nonsense is just gone. And the theorem is that the behavior, they're basically only 4, and 3 of them look very, very similar, and we have seen them. So for cycles like the triangle, it just is constant. It's just the line graph of a cycle is a cycle of the same type. So it's just constant. For the line itself, as we have seen, it just decreases number of vertices in each step and eventually goes to the bottom, the boring line graph, the empty graph, and then just constant. For the claw, so it's, by the way, called the claw because you can also illustrate it like this. Maybe you want to call it a bird track. You can also draw it like this. Sorry, this was wrong. Actually, it should be, give me another try. It should be like this. You can call it a claw, or a bird track or the D4 graph. Anyway, but this one is funny. It's not stable under the line operation, but it jumps to the triangle and then stabilizes. So it's effectively constant if you want. And everything else is just buff, explodes, and it's done. And that's it. And you could prove this really easily. So it's a fun exercise to do it. So this limit behavior in graphs is just so much simpler. And I totally like the theorem because it's one of those theorems where you think, oh, I could have discovered that. Basically, we did it together, right? So using some code, but effectively, of course, it's much easier to know the statement and then prove it instead of coming up with a statement yourself. So it's one of these. I could have done this, but actually, so certainly I couldn't have done this. That's for sure. But it's still a good theorem. It's much easier in discrete mathematics than it is in number theory or real numbers or whatever. And a kind of a fun fact you can prove using the theorem is that limit graphs, well, up a certain point, so we want to stay in the finite world. So with the limit graph, I really mean kind of after enough steps, you hit a finite graph. And it turns out that no matter what graph you start, unless you are in one of those three cases, which is a very, very restricted class of graphs, the limit graph will be a Hamiltonian graph. So you will find a Hamiltonian circle in the graph. And basically what happens is so Hamiltonian path is just visit every vertex exactly once, not to confuse with Eulerian, which would be visits every edge exactly once. No, every vertex exactly once. And what happens is that the line graph has just so many vertices, but even many, many more edges. So here in this example, we have quite a few edges here. Here in this example, we also have quite a few edges. So it gets more and more likely that it is actually Hamiltonian, and eventually it will be. So for some big enough number, the line graph will be Hamiltonian, which is kind of cool, and which you can somehow use to prove that most graphs are Hamiltonian anyway in the end, which looks quite strange because most of the small graphs you ever write down are not Hamiltonian. They have just more vertices than edges. Anyway, so this was kind of my big waffle of why discrete mathematics is so much nicer than whatever real mathematics. It's of course not true. It just really depends on what you want to do. But in this case, for example, there was divergence was not really an issue, and we had this nice kind of classification of potential patterns if we increase the number of iterations of the line operation, which I think is a cool statement. And you can discover it yourself by just testing a few small examples, which is what I did using a machine because I'm very lazy. But you could have done that by hand, right? So we could have done that by hand. Anyway, I hope you enjoyed the video, and I also hope to see you next time.